AI paper slap. Today, we are dissecting reversal Q-learning by Aditya Oberoi, Sihom Park, and Sergey Levine, and we are just going to jump right into it.
Let's do it.
So the paper introduces reversal Q-learning, or RQL, right, which is this new off-policy reinforcement learning algorithm designed specifically for training flow policies using prior data.
Exactly. And the core idea is that it treats those iterative flow refinement steps as like completely separate actions within an expanded MDP.
Right, which completely avoids the instability of backpropagation through time. And to make this work for off-policy offline datasets, RQL leverages the reversibility of deterministic flow ODEs.
Yeah, to generate exact virtual on-policy trajectories.
Then it applies unbiased multi-step returns to collapse that artificially expanded effective horizon, so it completely avoids those compounding value errors.
Which is huge.
It is, and the result is that RQL significantly outperforms state-of-the-art flow-based RL algorithms across like 50 highly complex simulated robotic tasks.
Yeah, it's honestly a remarkable piece of engineering. It solves this fundamental mathematical bottleneck that, I mean, if you look at the trajectory of reinforcement learning over the last 2 years, this is exactly the kind of structural breakthrough the community has been absolutely desperate for.
So let's frame that bottleneck for the machine learning engineers listening right now, because we've seen this massive explosion in iterative generative models, right?
Specifically, diffusion models and flow matching.
Yeah, and they are incredible at mapping complex multimodal distributions. Like, if you hand a flow policy a massive terabyte-sized data set of a robotic arm just doing totally random task-agnostic movements, it can model that underlying behavioral distribution perfectly.
Almost flawlessly, yeah.
But the moment you try to take that expressive prior and fine-tune it to maximize a specific reward using reinforcement learning, everything just breaks. Why is bridging that gap so punishing?
Well, the punishment comes directly from the iterative nature of the generation process itself. Like, think about a standard multi-layer perceptron, MLP policy.
Sure, the classic setup.
Right. It observes a state, performs a single forward pass, and outputs an action. Calculating the gradient to update that network based on a reward is super straightforward.
Just standard backprop.
Exactly. But a flow policy doesn't do a single pass. It generates an action by starting with pure noise and then iteratively refining it through an ordinary differential equation solver, an ODE solver over like 10, 20, or sometimes 50 distinct steps.
Yeah.
So if you want to train that policy using standard RL techniques to maximize a learned value function, you literally have to pass gradients through that entire multi-step chain.
And if you've ever tried to unroll an ODE solver for 50 steps and pass gradients through it, you already know the nightmare we are talking about here.
Oh, it's brutal.
You are forced into backpropagation through time, or BPTT,
Yeah.
and your memory footprint just absolutely explodes.
Right, because you have to store the activation graphs for every single intermediate step.
Yes, and worse, the gradients either vanish into nothingness or they explode into nans. It is a notoriously unstable computational process.
Unstable is almost an understatement when you're applying it to high-dimensional continuous control. Because of that instability, a lot of researchers have just pivoted entirely away from BPTT.
They just gave up on it.
Pretty much. They've sought refuge in regression-based techniques instead, methods like advantage-weighted actor-critic OAC or other forms of rejection sampling.
I really want to push back on those regression methods, though, because to me, they always feel like a massive compromise.
They absolutely are.
Like, you are bypassing the instability of backpropagation, sure, but the theoretical cost seems way, way too high.
You are identifying the exact flaw there.
Yeah.
Regression methods are compromised because they completely ignore first-order value gradients.
Right.
They basically reduce the value function to a simple zeroth-order black box oracle. They use the value function to just score actions, and then they basically filter or reweight the training data based on those scores.
So they aren't even really doing gradient descent on the action space.
Exactly. By doing that, you throw away the actual geometry of the Q function landscape. You aren't teaching the policy how to move its outputs up the gradient to achieve a higher reward.
You're just blindly hoping the data set already contains high reward actions that you can filter for.
Right, which is highly inefficient, and it fundamentally caps the optimization potential of the policy.
So basically, we are trapped between two really bad options. BPTT gives us the rich directional gradient information we need, but it just shatters computationally.
Yeah.
And regression gives us computational stability, but operates completely blind to the actual gradient landscape.
Exactly. Which brings us to the foundational framework of this paper, which is the expanded MDP.
Yes, let's get into this because the conceptual leap here is brilliant. If we can't safely backpropagate through the whole generative chain, we just break the chain apart.
We open the black box. Instead of treating the entire F-step iterative generative process as a single opaque action generation, the expanded Markov decision process reformulates it.
It augments the state space, right?
Yes. So our new state space, which they denote mathematically as S tilde, now includes three distinct things: the original physical environment state, the partially generated action at the current step, and the discretized flow time step.
Which essentially acts as a temporal counter from 0 to f-1.
Precisely.
Let's ground that in a physical analogy for everyone. If I'm an art critic evaluating a painter, the standard MDP approach is just staring at final finished painting and trying to reverse engineer how they created it.
Right, looking at the final output.
But the expanded MDP is totally different. I am stepping into the studio, standing right behind the artist, and judging every single individual brushstroke.
I love that analogy.
Right. And in this context, those brushstrokes are the individual Euler integration steps of the flow model. By framing it this way, we can actually deploy standard, off-the-shelf, single-step RL algorithms on the brushstrokes themselves, no unrolling required.
And the transition dynamics of this expanded space are fascinating because they are entirely deterministic while the flow is actually running.
Because the physical robot isn't actually moving yet, right?
Exactly. When you take an action in this expanded MDP, which is basically just the output of your network's velocity field for that specific brushstroke,
Yeah.
the physical environment doesn't change. All that happens is your partially generated action is updated and the time counter increments.
So you don't actually query the real environment simulator or receive a physical reward until the very final step.
Right, when the action is fully formed and executed.
Okay, the math maps beautifully to the theory there, but I'm sort of stuck here because our listeners are primarily dealing with off-policy, offline reinforcement learning, right?
Yes, that's the main focus.
We are trying to learn from a static data set, like a massive hard drive just filled with old, logged robot sensor data. And that data set doesn't have the brushstrokes.
No, it doesn't.
It only logs the starting state and the final action the robot took. So if we don't have the intermediate flow steps logged in our historical data, doesn't this entire expanded MDP thing just instantly break?
That is the first major theoretical wall the authors had to climb. You are absolutely correct. Offline datasets only contain final state action pairs.
Right.
You do not have the 10 intermediate noise refinement steps that your current untrained flow policy would have taken to get there.
Mm-hmm.
If you try to train an expanded MDP without that intermediate data, you essentially have no states to bootstrap your value function from.
And even if we magically had that data, like, let's say we did, wouldn't we just run into a massive cursive horizon?
Oh, a severely amplified cursive horizon, yes.
Yeah.
By treating every single flow step as its own MDP step, you've multiplied your effective horizon by the number of flow steps F.
So imagine your original robotic task takes 1,000 steps to complete. If you are using 10 flow steps to generate every single action, your new horizon is suddenly 10,000 steps.
Exactly. And in off-policy RL, which relies heavily on temporal difference or TD learning, an elongated horizon is usually fatal.
Because TD learning relies on bootstrapping, right?
Huh.
You are basically updating your current value estimate based on your future value estimate.
Precisely. And every time you bootstrap, you introduce a tiny, tiny amount of bias or error.
Right.
So when you stretch the chain of updates out to 10,000 steps, those TD target errors accumulate at every single step. Over that much longer chain, those biases compound so aggressively that the value function just straight up collapses.
It overestimates some states, underestimates others.
And eventually it just outputs total garbage.
Okay, so the expanded MDP gives us access to single-step gradients, but it introduces two pretty catastrophic problems. First, missing intermediate dataset states. And second, a horizon so long it destroys TD learning.
Right.
So let's look at how reversal Q learning systematically dismantles both of these walls, starting with the missing brushstrokes.
Yeah.
If our dataset only gives us the final physical action the robot took, how does RQL conjure the intermediate states? Do we just, run the math backward to hallucinate what our network would have done?
We do exactly that, and we are allowed to do that because of the underlying mathematical properties of continuous normalizing flows. Flows induce diffeomorphisms.
Okay, let's define that for the audience real quick. A diffeomorphism is a smooth mapping between two mathematical spaces where the inverse mapping is also smooth.
And that property is the absolute key differentiator here. Because of that smooth projection, the flow ODE is completely deterministic and reversible.
Wow, okay.
Contrast this with standard denoising diffusion probabilistic models, or DDPMs. Those rely on stochastic differential equations. They literally inject random noise at every single step.
Right, so you can't just take a final image and perfectly run a stochastic process backward to find the exact noise vector that generated.
Exactly, because the randomness destroys the path history. But with deterministic flow matching, there is no injected noise during the generation steps. The path from noise to action is this rigid two-way street.
So we literally just flip the sign. Like we start at the final action, logged in the offline dataset, set that as our endpoint, reverse the sign of the velocity field, and run the Euler method backward to time step 0.
That is the exact operation, yes. RQL generates virtual trajectories of what the current policy would have produced.
That's wild.
We use the offline data to ground the endpoints, and then we just hallucinate the exact intermediate steps required to get there.
Yeah.
It solves the missing data problem with total mathematical rigor.
Okay, so we have our brushstrokes, but we still have that expanded horizon that is F times longer, right?
Yes.
And in normal off-policy RL, if you want to bypass a long horizon, you usually try to use multi-step returns. You basically look several steps ahead to update your value function all at once.
Right.
But doing that normally requires really complex importance sampling to correct for the fact that the historical data doesn't match your current policy.
And important sampling in continuous action spaces almost always blows up in variance.
Exactly. It's super unstable. So how does RQL defeat the curse of horizon without exploding?
This is where the paper's central elegance really shines. Look closely at the virtual trajectories we just generated. We didn't pull them from an off-policy historical log. We hallucinated them by running our current flow policy's velocity field backward. Because of that, these trajectories are, by definition, fully deterministic and exactly on policy.
Whoa, I see it. Because we generated them using our current network weights, they aren't off policy at all. They perfectly represent what our policy would do right now.
Exactly. And because they are entirely on policy and deterministic, the multi-step returns become completely unbiased and zero variance.
Wait, really? Zero variance?
Zero variance. You don't need any important sampling corrections whatsoever. You evaluate the value function at the very end of the flow trajectory, and you back up those gradients directly to the beginning.
Okay. To visualize why this matters, let's use an analogy. Standard TD learning over an elongated horizon is kind of like playing a massive game of telephone.
Yeah, that's a good way to look at it.
Every time you pass the value backward one step, every time you whisper to the next person, a little bit of distortion is introduced. After 10,000 whispers, the message is totally unrecognizable. What RQL does with these deterministic on-policy trajectories is replace that entire game of telephone with a perfectly unbendable, rigid steel pole connecting the first person to the last person.
That is a perfect visualization. Because the physical mapping is deterministic and evaluated on policy, moving the pole at the end translates the exact same movement to the beginning with absolutely zero distortion or variance.
It effectively collapses the value horizon from T times F all the way back down to just T.
You completely neutralize the curse of horizon.
Yeah.
You get all the computational stability of the expanded MDP, meaning no backpropagation through time.
Right.
And you get the rich first-order gradients, all without the fatal penalty of an elongated TD chain.
That is just an incredibly slick piece of architecture. But for the ML practitioners listening who actually want to implement this, let's look under the hood at the specific loss functions. How is this actually coded?
Sure. So the policy loss in RQL is basically structured around two distinct components that have to balance each other out. The first is value maximization. Since this is a Q-learning framework, we need a mathematical operator to approximate the maximum expected return, the highest possible reward. RQL uses an expectile loss for this, controlled by a hyperparameter called kappa.
I want to spend a second on expectile loss, actually, because it has become pretty ubiquitous in offline RL ever since implicit Q-learning popularized it.
He really has.
Why use expectile loss instead of just simply querying the Q network for the maximum action?
Because querying the Q network for actions in an offline setting is incredibly dangerous.
How so?
If you ask a neural network to maximize a value, It will inherently seek out actions that it hasn't seen in the training data. Its uncertainty around those out-of-distribution actions often manifests as highly optimistic, inflated value predictions.
Ah, right. It hallucinates a massive reward for something stupid.
Exactly. And if you optimize against those false peaks, the policy just completely breaks down. Expectile loss allows you to estimate the maximum value purely using the actions that actually exist in your dataset.
By asymmetrically weighting the TD errors, right?
Yes. It penalizes positive TD errors differently than negative ones, effectively skewing the average toward the maximum observed values without ever needing to query the policy for hypothetical out-of-distribution actions.
And the authors highlight that tuning that expectile parameter, kappa, is absolutely critical. Like if kappa is 0.5, you are basically doing SARSA.
Right, just taking the mean value of the data.
But as kappa approaches 1.0, you are leaning heavily into strict Q-learning, aggressively seeking the maximum value. They actually found that a high kappa, specifically around 0.9, performs exceptionally well for their benchmarks.
It does.
And that makes total sense when you look at the datasets they used from OG Bench. Those datasets are just absolutely full of highly suboptimal, task-agnostic, random robotic flailing.
Tons of useless noise.
Yeah. You want the algorithm to forcefully extract the sparse, high-value behaviors from that slop. So setting kappa to 0.9 to demand more RL and less averaging is just the scientifically correct move.
You are absolutely right. However, you can't only maximize the value, even with expectile loss protecting you.
Right, there has to be a regularizer.
Exactly. If you push the velocity field too hard to maximize reward, it will still eventually drift out of the underlying data distribution and collapse. To prevent that, the second component of the policy loss is behavioral cloning, or BC regularization.
So this acts as the anchor, keeping the policy grounded in physical reality.
Yes. They add a standard flow matching loss term, controlled by a hyperparameter alpha. This ensures that while the velocity field is being aggressively tweaked to climb the Q function gradient, the actual distribution of generated actions doesn't deviate too far from the safety of the prior dataset.
And in their ablation studies, the authors point out that alpha is basically the single most critical hyperparameter to tune when migrating this algorithm to different tasks.
Absolutely.
Right.
Getting that balance right is key.
And I think it's important to briefly mention that RQL pairs this core loss with some very robust modern RL stabilizers, too. Specifically, action chunking and pessimistic critic backups.
Yes, very important.
Action chunking means the network doesn't just predict the immediate next action, right? It predicts a short sequence of future actions. This massively reduces the high-frequency jitter you often get in continuous control.
Right.
And pessimistic critic backups involve training an ensemble of critic networks and taking their lower bound to aggressively punish any lingering value overestimation.
Those are just minor details either. They are crucial engineering decisions that take an elegant mathematical theory and force it to actually converge in a chaotic simulator environment.
Which brings us to the empirical gauntlet. Mathematical theory is beautiful, sure, but mathematical theory has a funny habit of completely falling apart the second you drop it into a physics engine.
It really does.
When they actually forced this to control complex robots, did the zero variance trick hold up?
It did more than hold up. It completely dominated. They tested RQL across 50 diverse robotic tasks from the OG Bench suite.
And we are not talking about simple grid world problems here.
No, these are brutal environments. You have fine-grained combinatorial puzzle manipulation, where a robotic arm literally has to stitch together logic to arrange blocks with tight physical constraints.
Yeah, all the way up to long horizon, high-dimensional locomotion tasks like humanoid maze large, where a multi-jointed agent has to walk through a complex labyrinth.
And across all 50 of those environments, RQL achieved the highest average offline RL performance. It decisively beat out a whole slate of state-of-the-art baselines.
Wow.
To give you an idea of the landscape it conquered, it outperformed BDPO, which is an algorithm that attempts to use complex hierarchical value functions. But BDPO tends to struggle really heavily with the fine-grained control required in those combinatorial tasks.
It also beat IFQL, right?
Yes. IFQL tries to get around the BPTT problem by relying heavily on rejection sampling. But as we discussed earlier, rejection sampling essentially throws away massive amounts of useful gradient data.
Making it way too inefficient to solve the harder humanoid tasks.
Exactly. And perhaps most importantly, RQL handily beat FBR. FBR is a method that stubbornly tries to brute force its way through backpropagation through time.
Right, just taking the computational hit.
Yeah, and it works decently on simple tasks, but on high-dimensional systems, the instability of unrolling the ODE solver just causes its performance to completely plummet. RQL avoided all of those pitfalls.
To me, honestly, the most compelling piece of empirical evidence isn't even the baseline comparisons, it's the ablation study.
Oh, absolutely.
They created an intentionally hobbled variant of their own architecture called TFQL. TFQL uses the Expanded MDP framework, and it hallucinates the virtual trajectories backward perfectly, but it strictly removes the horizon reduction trick.
It throws away the rigid steel pole.
Exactly. It forces the critic to learn over the massively elongated T times F horizon, step by painful step.
And the results of that ablation are stark. They empirically validate the entire paper. On several complex tasks, TFQL just completely collapses. It fails to learn anything meaningful whatsoever.
It proves that the expanded MDP alone just isn't enough. Without the zero variance multi-step return to collapse the horizon, the compounding TD error fundamentally destroys the value function.
Right.
That horizon reduction trick isn't just like a neat optimization to speed up training. It is the absolute secret sauce required for this architecture to survive at all.
It is the mathematical linchpin. By combining deterministic flow reversal with on-policy multi-step returns, they've basically engineered a bridge over the two most fatal pitfalls of off-policy generative reinforcement learning.
This paper undeniably proves RQL's dominance in continuous robotic control. But for everyone listening, I want to pivot to the broader implications of this architecture before we wrap up.
Sure.
Because deterministic flow reversal isn't just a robotics trick, right? It is a universal mathematical property of flame matching.
That reality raises a massive field-altering question.
Yeah.
If you look at the absolute frontier of AI research today, one of the biggest open problems is how to apply reinforcement learning from human feedback, RLHF, directly to pixel space.
Exactly. Fine-tuning massive billion-parameter text-to-image or video generation models to optimize for a specific, non-differentiable reward function.
Like aesthetic quality, prompt alignment, or physical realism.
Right. And doing that is an absolute nightmare right now.
Because they face the exact same mathematical wall. If you want to use RL to teach a diffusion or flow model to generate better images, you literally have to unroll the generation process for 50 steps and try to backpropagate a reward through it.
And as we know, that is catastrophically unstable.
Right.
But if deterministic flow reversal allows us to accurately map out the generative trajectory, and unbiased multi-step returns allow us to collapse the effective horizon without ever touching backpropagation through time.
You see where this is going?
Could machine learning engineers leverage this exact same expanded MDP reversal trick to dramatically improve the fine-tuning of generative visual models?
I mean, the math strongly suggests it is possible. If you can define the state space of a partially generated image and log the flow steps, there's basically no theoretical reason why RQL's mechanics couldn't apply.
Could we effectively perform RLHF on pixels? Like stepping into the studio to evaluate the brush strokes of a video generation model without the whole system shattering under memory constraints?
That is a massive question to ponder.
It really is. When we talk about evaluating an AI agent, we almost exclusively focus on judging the final, completed painting. But maybe the key to unlocking the next massive leap in generative fine-tuning isn't found in the final image at all.
Right.
Maybe it's found in mastering the mathematics of the brushstrokes.